we have a very good result which says that every closed subset of a compact metric space is compact. Every closed subspace of a compact metric space is compact. So let us take here I have this is my suppose a compact metric space X and this blue, okay, this is my closed set Y. It is not necessarily it is a circle or it is just I have mentioned it because uh, just to show you, it is not necessarily you can take the circle or something. As I mentioned that the ball or ball are quite different. The shape of the ball are quite different. It should not be a circle or a sphere. Okay, it depends on the metric, what kind of the metric we are considering. So the shape of the ball will be changed. So just to show you, I am considering this is my closed subset of the metric space X. Okay, and then we will have to prove that this closed set is also compact. Okay, so it's a very simple. So let Y be a closed subset of a compact metric space set, and F is equal to, this is the collection of open subsets of Y, okay, by sets open in X. Okay, so this is the collection of open subsets of open cover. So here is these are dotted circles, you can say. These are the open sets. These are open sets in X. Okay, and then you take the collection of all these dotted lines, which is equal to your F, which is equal to G alpha. So this is your G1, G2, G3 and so on and so forth. Okay, and then we can see that this Y is nothing but it is the subset of the union of all these sets. So this Y is a subset of union of all G alpha, where G alpha is open in X. Now we can take then F star is equal to F union. So we can take because we are taking the collection. So F star, we can take F all these one and the complement of this one, and that is to say this portion. The complement of this means this portion. So because this set Y is your closed set, so the complement of this is open. Okay, it means that you can add. So F this collection, okay, which is covering this Y, and okay, so this is the open set. Arbitrary union of open set is open, and this is your open. Okay, so and if you include this set, it will cover the whole X. So since because Y is so weak, it will cover the whole space. Since X is compact, then this F star, which is equal to F star is equal to F union complement Y. This is an open cover of X. And since Y is compact, this new open cover, okay, has a finite subcover, say C star. If this finite subcover C star contains the complement of Y, that is, if X is equal to G alpha 1 union G alpha n union complement of Y, okay, then discard this G alpha Y, discard this open, this set, since it covers no point of Y. Otherwise, leave the sub collection alone, that is C star is equal to G alpha 1, G alpha 2, G alpha n. Then we can see that Y is the subset of G alpha 1 union G alpha n, where G alpha is n in F. And this means that C star, okay, is a finite subcollection of F that covers Y. And then by the previous lemma, we can say that Y is compact. So this way we can prove that every closed subspace, every closed subset of a compact metric space is compact. Now, we can see that very easily any intersection of compact sets is compact. Any arbitrary intersection of compact set is compact and finite union of compact set is compact. Now, what about the arbitrary union of compact set is compact? Okay, try it to yourself and it is given in the exercise. Then we have a very interesting property which is called finite intersection property. So, a collection C whose elements are C1, C2, C3 and so on of subsets of a metric space X. So, a collection of subsets of a metric space X is said to have the finite intersection property if every finite subcollection of C has non-empty intersection. That is, if for every finite subcollection C1, C2, Cn of this collection, we have the intersection of Ci's is non-empty. Let us consider an example. So, consider the collection of open intervals 0, 1, 0, 1 half, 0, 1 over 3, 0, 1 over 4 and so on. Okay. So, this is the collection of open intervals. And then we can see that this collection of open interval has the finite intersection property. That is to say, if you take any finite collection, you take this and take the intersection, it is non-empty. You take this up to here, it is non-empty. You take from 0, 1 over n and you take 0, 1 over m. You take the intersection, it is non-empty. So, if you take any collection, it is non-empty. And you can also see that if you have a 0, a1 intersection 0, a2 and 0, am, okay, then the intersection this is equal to 0, b, where b is the minimum of a1, a2, a3, am and it is greater than 0. Okay, so this intersection is non-empty. Therefore, any class C has non-empty intersection, even C itself has an empty intersection. Okay, and thus C satisfies the finite intersection property. Similarly, we can consider the collection of closed intervals. Here we have taken the open intervals. So, let us take C is the collection of closed intervals. So, here is minus infinity to minus 2, minus infinity minus 1, minus infinity 0, minus infinity 1, minus infinity 2 and so on. So, these are the closed sets, keep in mind. These are the closed sets in R. Then C has an empty intersection. Okay, that is the intersection of Cn is equal to empty, where Cn is equal to minus infinity to n of this one. But if you take any finite subfamily of this family, okay, we will see that it has a non-empty intersection. So, C satisfies the finite intersection property. So, again I am repeating, finite intersection property means if you have a collection of subsets, whether the sets are open, closed, open, closed, open, open, whatever it is. So, a collection of subsets of a metric space is said to have the finite intersection property if every subcollection has non-empty intersection. Okay, here I have given the family of open intervals, and here is the family of closed interval, and both families have a finite intersection property. Now, is there any relation between the finite intersection property and the compactness of the space? Yes, we do have. And the following theorem expresses that a metric space X is compact if and only if every collection of closed sets in X closed sets in X having finite intersection property has non-empty intersection. Okay. So, a metric space X is compact if and only if every collection of closed sets in X having finite intersection property has non-empty intersection. Let us prove this one. So, let X be a compact metric space and C is equal to C alpha. Okay, alpha lies in lambda and lambda is any index set. Okay, so C be any collection of closed sets in X having finite intersection property. Having finite intersection property means if you take any finite intersection of the sets of C, it is non-empty. Okay, then we claim that the whole intersection is non-empty. So here is if here the sets are closed, okay, the whole intersection is non-empty. If the finite intersection is non-empty, then the whole intersection is non-empty. The condition is that the Cn must be closed subsets of a compact metric space. Okay, or closed subsets. Okay, then the space X is compact. So assume that this is equal to empty. So by De Morgan theorem, we can see that the union of, so we can take the union, complement both sides. So here is we have the union of X, okay, the complement of Cn, okay, which is equal to the complement of the intersection of this in X, which is equal to your, because this is your empty set, so this is equal to your whole X. This implies that this Cn is what? Cn is your closed set, and this is what? This is the complement of closed set, which is your open set, and the union of open set is equal to whole space. So the collection of the elements of this form, they forms an open cover of X. Okay, and since X is finite, so this has a finite subcover, say C star, which is equal to the complement of C alpha I runs from 1 to n, say. Then X is equal to union of I runs from 1 to n, the complement of C alpha I. And this implies that, we can see that this implies that X minus the intersection of this is equal to who? It means what? It means that this, the intersection this is equal to your empty set. This is your empty set. This shows that C does not have the finite intersection property, because C we are considering is a collection of closed sets having finite intersection property. But here you see this is the intersection is empty. Okay, so this shows that C does not have the finite intersection, which is a contradiction to our hypothesis, and therefore the whole this intersection, what we are assuming that this is empty, it is not true, it is a non-empty. Now for the converse, assume that X is not compact. Now we want to prove that X is compact. Suppose X is not compact, then there exists an open cover, okay, G open cover F, whose element of G alpha open sets in X, which does not have any finite subcover. That is, for any finite subcollection G alpha 1, G alpha n of F, we have the union of G alpha I is not equal to X. Now take the complement both the side, then X minus this is equal to not equal to the empty set. It means that this intersection is not empty set. Now for each alpha, let C alpha is equal to the complement of G alpha. But G alpha is what? G alpha I, they are open set. This is your closed set. So this is your C alpha is closed. And now since the intersection of C alpha I runs from 1 to n, so this is the finite intersection of closed sets, because this is non-empty, so this is non-empty. It means that this collection is a collection of closed sets having finite intersection property. Okay, and by the hypothesis, a collection of closed sets having finite intersection property has a non-empty intersection. It means that because this collection of closed sets having finite intersection property is therefore the whole intersection is non-empty. Now, on the other hand, since f is equal to g alpha, this is a cover of X, and therefore the union of G alpha must be equal to X. And so we can take the intersection of C alpha is equal to the intersection of the complement of this, because we have defined C and alpha is equal to X minus G alpha. So we can put, and this is equal to X minus the union of this one. But you will see that this is equal to your empty set. Okay, so this is your empty set. Why it is in? Because the X is equal to the union of G alpha. So they both are same. So this is your empty set. So here we are saying that the intersection of C alpha are, so okay, the whole intersection, okay, of C alpha is equal to empty, and here we have proved that the intersection is non-empty. So this is the contradiction, and therefore hence X is your compact set. Now, as a corollary, we can have a metric space X is compact if and only if every collection C of elements F1, F2, F and so on of subsets of X having finite intersection property, the intersection of closure of F and F is in this set of their closure is non-empty. So instead of taking the closed sets, we are taking here is the closure of the set F. So let F1, F2, Fn be a finite subcollection of C such that the finite intersection is non-empty. Since each Fi is a subset of closure of Fi, because this intersection is non-empty and this intersection is a subset of the intersection of the closure of Fi, and therefore the intersection of this is non-empty. Okay, and hence C prime is equal to C1 closure, F1 closure, F2 closure be a collection of closed sets having finite intersection property, and then by previous theorem we can see that this intersection is non-empty. Okay, so this we have proved. Now as an exercise we can have XD be a metric space such that every subset of X is compact. Every subset of X is compact, then prove that X must be finite. So here the proof I have already given, and what we have mentioned that any intersection of compact set is compact, any finite union of compact set is compact. So this is also we have given the proof, and but you try to solve these exercises by yourself. If you are unable to do it, then try to find it. Otherwise, don't do it by don't see the proof first. Try to see the proof. Try to solve these exercises by yourself. So I stop this talk here, and we will discuss some other things related to the compact set as sequentially compact Bolzano-Weierstrass property, and then the equivalence of all these properties or these definitions. So thank you very much.